basic principles, in fact, of physics don't apply. We're not talking about some far-flung imaginary world, but at our own atomic level.
Yeah, it's a world governed by quantum mechanics, where one thing can be in two places at the same time. The Quantum Control Laboratory at the University of Sydney has been set up to investigate quantum physics and develop technologies. Dr. Michael Biercuk is the primary investigator at the laboratory, and he joined Dr. Karl to explain this very strange world that physicists are exploring.
He has stuff in his laboratory that is colder than the coldest spots anywhere in the known universe, out there in deep space. And number two, he's not just talking about it, he's building stuff. He's actually building quantum stuff that will be what we'll be using in the future.
For decades, we thought it was just strange math. Even Einstein made fun of some of these concepts. The greatest minds of the 20th century just mocked it. And what we've learned over the past couple of decades is that all of these phenomena are real, and we can measure them in laboratories, in real laboratories like mine.
So this isn't just theory that you can crunch the numbers. You're actually doing this work at an atomic level.
That's right. We can actually do experiments to observe this weird stuff and exclude all the other possible explanations that we've come up with. And so people have been excited by this, obviously, people like me thinking about building technology, but others have said, well, maybe some of these phenomena may be present in life, in biological systems. And there's some very good work going on now that suggests that some of this weird quantum physics, things being in two states at once and linked together over vast distances, actually underlies the way that certain birds can migrate north to south. That there's a quantum physical process involved in their retina that makes them able to effectively see the Earth's magnetic field. The Earth, the planet Earth, has a big magnetic field associated with it. We don't see it unless we have a compass. So this is a phenomenon called the avian compass, that we think it may be some of these weird quantum effects that allows them to actually, with their eyes, see the direction of the magnetic field to help them fly straight north.
So it's almost using another dimension through their eyes, not just as we would see the world. They have this.
Well, yeah, there are lots
added
of
capacity.
How does it work?
Well, so we're not exactly sure, but the speculation is that there's a chemical reaction in the eye of this bird. And that chemical reaction involves a particle of light, a photon coming in, just like the light that we see. It makes a pair of electrons, the charge carriers that we talk about when electricity flows. It splits them up. And then they want to recombine. But they can only recombine if the quantum coherence, that is the quantumness of the system, is maintained. And one way you can change that is by having a magnetic field. So if you have the magnetic field oriented in just the right way, these particles, these electrons can recombine, and it makes a signal that's detectable in the eye of this bird. Otherwise, it sees something dark, and so it steers for maybe the bright bits.
How do you do that in a laboratory?
We can actually trap, in my laboratory, single atoms in a special kind of electromagnetic bottle called an ion trap, and then we can manipulate the quantum mechanical state of that atom to make it either do useful things or to study, for instance, how some of these avian compass processes might work.
But I should point out, Andrew, that his building is a building within a building, that the floors that he stands on, are 1.5 meters thick of concrete, that when they built the building, they had to compensate for underground railway lines 2 kilometres away. So what sort of stuff are you trying to build in this amazing super high-tech world that you're in?
Yeah, it's not just all for fun and vanity, right? We have tried to build this kind of building, a really, really special laboratory facility, because it's always, well, for a long time now, it's been the buildings that we work in rather than our imaginations that have limited what we can achieve.
But you're trying to establish the perfectly controlled environment.
That's absolutely right, because we know that we're sitting here today, we're not experiencing all these weird quantum physical effects that appear in the theory. We are described by classical physics. So something happens to turn quantum things into classical things. That's something that people study in our community. But if you're trying to build technology with quantum physics, anything in the world, Wi-Fi, all that, makes it fall apart.
Would the best laboratory not be then in some sort of vacuum, as in
up there
in space?
Well, so the amazing thing is we actually try to build that in our laboratories. We have special vessels called ultra-high vacuum chambers that we evacuate to pressures that are lower than space out near the space station. Not quite as low as what you find in deep intergalactic space, but lower than near Earth orbit. And that's the system in which we can trap these individual atoms and then manipulate them to our ends.
In your laboratory, you're building...
We are building real technologies, and the real crux of our research focuses on something called a quantum simulator. So it's a special computer that uses this weird physics that underlies, all reality, in order to process information in a way no other computer could work. So to solve problems that no other computer could ever conceivably solve. You could never build, ever, a supercomputer with capabilities matching some of the things that we're building now. And that's because in quantum systems, there's something called the complexity of information representation. It's a little bit of a techie topic, but it really says that it's very hard to put all this stuff in memory. And in fact, to build a system that was just as powerful as one of the things that my team and my colleagues at NIST in the US built a few years ago, you would need a supercomputer bigger than the whole universe.
Bigger?
Bigger than the universe.
It would need more atoms in it than there are atoms in the universe.
That's just to store the information in memory. It's just not possible.
But if you build it as a quantum device...
That's right.
You could build it. You wouldn't have to pulverize the whole universe to do it.
We've already built a system and we've done the most basic checking, does 1 + 1 = 2 kind of questions, and it works. And so it's really promising to say how that can be turned into a computer that can do useful things. That's a long time away, but still.
It is fascinating indeed, and that's bigness beyond our comprehension. Karl, Michael, thanks so much.
Thank you so much.
Oh, it is fascinating, but gee, it's mind-boggling.
Oh, it hurts my head. It hurts my head. I did, though, at one stage have an ambition to be a marine biologist. And you know what? Apparently there are some young Indigenous women from North Queensland who are also having their horizons broadened. A program called Deadly Science Getaway is giving them the skills and confidence to pursue further education and dream careers.
Well, the latest venture of the joint Queensland Government and James Cook University scheme was a trip to Orpheus Island Research Station to learn about marine biology. Our story produced by Tom Edwards.
The program is targeting these extraordinary young women who come from Cape York and Palm Island, and what we want them to know is that there is this incredible world of opportunity available to them. And so we bring them here and we wrap them up in this incredible world filled with marine biology, nature, incredible women, and a safe and supportive peer environment where they can learn about themselves, do really challenging, amazing things, discuss careers and talk about future hopes and dreams.
I came back to the camp because I like the snorkeling, meeting new people, and it reminds me of home. We always swim, and yeah, we always ran the jetty and do some snorkeling around there.
And it helps keep it not be foggy. We have a really fun camp this year. We've been out on the reef learning about the basics of the difference between hard and soft corals, what a bleach coral looks like compared to a healthy coral. We've been checking out how the fish use the coral as habitat, and also learning about how sea cucumbers clean the sand and act like the kidneys of the reef.
Look here, look out. Pen.
Orpheus Island. It's quiet, peaceful, nice people. I wanted to come because there's lots of great experience learning new things, meeting new people.
Where they come from is very remote and isolated. The window of opportunity is very narrow, so you might ask someone from community what you want to be when you leave school, and 9 times out of 10 they will say a plumber, work in the health clinic or childcare. The good thing about trips like this is that it's just opening up further studies, university, that there's other things outside of working in the clinic or childcare or at the shop.
We see their attitude about themselves and life in general go up, and we see them wanting to engage more with school and starting to think about careers and even decide on careers that they're going to pursue. It's so extraordinary to see them grow and change.
It's a great program, and as we were saying, no better classroom than the outdoors.
Well done.
Now let's talk sport. Georgie joins us, and let's analyse the disaster that was Australia's batting yesterday.
Yes, disastrous indeed, guys. It really was a tale of two teams. Disaster for the Aussies. On the other hand, joy though.